Okay, this is Algebra 1, Lesson 29. We're going to talk about exponents today. So we're going to start off with negative exponents. We can find an alternative way to write 1 over 5 squared and 1 over 5 to the negative 2. So let's look at that. So we have 1 over 5 squared, yes, is equal to 5 to the negative second power. Let's look at 1 over 5 to the negative 2 is equal to 5 squared. Okay, so let's look at the formal definition of that. It says if we will use x and n to represent the base and the exponent, x will represent the base and n will represent the exponent. So if n is any real number and x is any real number that is not 0, then 1 over x to the n is equal to x to the negative n power. So let's look at some examples. Write this definition down. You need to have it in your notes. Okay, let's look at some examples. Let's look at example A on 29.8. If we have 1 over 3 to the 4th, we can simply move the exponent, the base, from the denominator to the numerator by doing the opposite of its exponent. Exponent's positive 4, we move it, we just change the sign to its opposite, negative. Look at 7 to the negative 2. Okay? Isn't this 7 over 1? What's the reciprocal of 7 over 1? 1 over 7, and then we change the sign to its opposite, 7 squared. Let's look at 1 over 5 to the negative 8. Isn't that, don't look at the exponent, it's 1 over 5. What's the reciprocal of 1 over 5? It's 5, and you simply change the exponent to its opposite, which is positive 8, or 5 to the 8th. We don't put the positive, this is implied. I'm going to erase this definition. Okay, let's look at another one. Let's look at 6 to the negative 3. Isn't that the same thing as 6 over 1? And the reciprocal of 6 is 1 over 6. We take its exponent and change it to its opposite, which is 3. Now we have 1 over 6 cubed. So in A, we moved 3 to the 4th from the denominator to the numerator, and we changed the sign of the exponent from a plus to a minus. B, we moved it from the numerator to the denominator, and we went from a negative exponent to a positive. We simply did its opposite. So the formal definition of x to the negative n is stated in the box above, and we will now look at a definition informally stated. So look at the little box in the middle of page 121. It says a number or a variable that is written as an exponential expression can be written in reciprocal form if the sign of the exponent is changed. So the exponent is positive, the exponent is negative in its reciprocal form. If the exponent is negative, then the exponent is positive in the reciprocal form. So let's look at this one. We have 3 to the negative 2. Okay, what's the reciprocal of that? 1 over 3. In its normal form, it's a negative, so we change it to a positive. So we have 1 over 3 squared. And then we can simply do 1 over 9. Right, so doesn't that mean 3 times 3? Let's look at the example from 29.2. So we have 1 over 3 to the negative third. What's the reciprocal of 1/3? It's 3. To put it in its reciprocal form, we change the opposite of the exponent, 3 cubed. What is 3 cubed equal to? 3 times 3 times 3, or simply 27. Now remember, reciprocal is not the same thing as opposite. So we do the reciprocal of this number and take the opposite of the exponent of the base. Okay, the exponent, not the opposite of the number. So let's look at another one. So let's look at this one. This is where negatives tend to give us fits sometimes. We have to remember what we're doing. Here we said this is the same thing as negative 3 over 1. Remember, this negative is protected by this parentheses. What is its reciprocal? It's 1 over negative 3. What's its exponent? It's negative 2, so the opposite of its exponent is positive 2. Or you simply have 1 over negative 3 times negative 3 And we should know a negative times a negative gives us a positive. So it's 1 over 9. So let's go back and remember, what is our product rule for exponents? We said if m and n are real numbers, and x is not equal to 0, then x to the m n, remember when two variables next to each other means multiplication. I'm sorry, m times x to the n is equal to the x to the m plus n. Okay? So let's look at this one. Doesn't matter what sign they are. That is our product rule. So you need to write that down. X to the m times x to the n equals x to the m plus n. So let's look at x to the negative 5 times x squared equals what? Well, this imply multiplication because there's two variables next to each other. You have to have the same base, which you do. You simply add the x on. Negative 5 plus 2. Then it goes back to, what are integer rules? What is negative 5 and positive 2? It's going to give you x to the negative cube. If we want to make that positive, we can change it to its reciprocal, and it's 1 over x cubed. Or we can simply leave it in this format unless they tell us otherwise. Okay? Let's look at another one. If I have y to the 7th, y to the 5th, y to the negative 2. That simply is going to say y to the 7 plus 5 minus 2. 7 plus 5 is 12, minus 2 is 10. So you have y to the 10th power. Okay? Let's look at another one. P to the 10th power times p to the negative 15. You simply have p here, have same base, and you do 10 plus a negative 15, or 10 minus 15, which gives us p to the negative 5 power. Okay? Let's look at one that's a little bit more complicated. So let's simplify x to the 4th, m squared, x to the negative 2, then m to the negative 5. The first thing I'm going to do is I'm going to put like exponent bases together. I'm just rearranging. Remember, my commutative property says a times b is equal to b times a. So I can rearrange these without changing it. All I did, I didn't drop anything, I didn't add anything, didn't multiply. I just rearranged them. I moved this over here and this over here. So now I've got my two bases together, which is x to the 4 minus 2 times m squared minus 5, which is 4 minus 2 is x squared, and 2 minus 5 is m to the negative 3rd power. So you still use your exponent rules. It's a positive 2 and a negative 2, which give you a negative 3. Okay? Let's look at example 29.5. Simplify. X to the negative 2, y to the negative 6, y to the 5th, x to the 4th, z, x, z to the 5th. If there's no exponent, it's a implied 1. I'm going to rearrange these. So my like terms are like. So then I have x to the negative 2 plus 4 plus 1, y to the negative 6 plus 5, z to the 1 plus 5. Then I simply get 2 and negative 2 and positive 4 is positive 2 plus 1. So x cubed, y to the negative 1, z to the 6th power. Okay? Now let's look at zero exponents. So we know that 1 is equal to any number divided by itself. Yes? Isn't that 4 squared divided by 4 squared gives us 0? Now we can simplify the expression by moving the 4 squared from the denominator to the numerator, right? We said if we move it to the numerator, we take the opposite of its base. Now don't we have a product of exponents with the same base? Yes, we simply have 2 minus 2 equal 4 to the 0 power. And what did we say? 4 squared divided by 4 squared is 1. So therefore, 4 to the 0 power must equal to 1. because it's like dividing 4 squared divided by 4 squared. So let's look at this one. X plus y plus z squared raised to the 0 power is equal to 1. You're like, how is that? Well, because everything is raised to the 0 power. When we have a base raised to the 0 power, so we multiply the exponents. So this is 1 times 0, x to the 0. Yes? So everything in here is raised to the 0 power. It doesn't matter what it is. You're going to get 1 as your answer. So our definition here, which you need to write, says if x is any real number that is not 0, then x to the 0 power is going to equal to 1. Just like we got p m raised to the 0 power, that's equal to 1. And then we had p x to the negative 4 raised to the 0 power, we get 1. So let's simplify this expression over here. Let's do example 29.6. What does it say? It says that I have x squared, y to the fifth, y to the negative 2, x to the negative 2. So I get y to the third, x to the 0 power. What is x to the 0 power? It's y cubed times 1, or simply y cubed. Right? Because x to the 0 is 1 if x is not equal to 0. Let's look at this next one. M to the fifth, b squared, times m, b to the negative 2. I add my exponents, that's m to the 6th power, b to the 0. Or simply m to the 6th times 1, or m to the 6th. Okay? Since we must not use the expression 0 to the 0 power, it is necessary in problems such as A and B to assume that the variable with the 0 exponent is not 0. Further in the problem sets, we will assume a non-zero value for any variable that has a 0 exponent. So we're going to assume going forward that any variable that we use to the 0 power is going to be a non-zero number. So let's look at 29.7. We have to use the distributive properties. Okay, so let's use the distributive properties. So we've got x to the fifth, y to the 0, z times p to the negative 3, z to the 0, minus 4, whoops, running out of juice here. So, minus 4, for x to the negative 5, and z to the negative 1. So we have to distribute all of this to every term inside this parentheses. And if you see, there's 2 terms in these parentheses. Okay? So we're going to have x to the 5th, y to the 0, p to the negative 3rd, and z to the 1. Because you have z to the 1 power plus z to the 0 power, which is 1. Then it's minus 4 x to the 0, positive 5 and negative 5, y to the 0, and z to the 0. Because you have positive 1 and a negative 1. Together, they equal 0. Alright, so let me make this a little darker. You can see that a little better. Okay, so then we simply combine. This becomes 1, so this is x to the 5th, p to the negative 3rd, z, minus 4. Because all these are 1. 1 times 1 times 1 times 4 is just 4. And that's simply our answer. So we use the distributive property. So let's simplify. Let's do a couple more examples. So let's look at, what if I have 2 to the 0? What is that equal to? Well, we said anything to the 0 power, it doesn't matter what it is, it's 0. Negative 2 to the 0 power. Remember, this is negative 1 times 2 to the 0 power. So that's 1 times negative, which is a negative 1. Okay? C is negative 2 raised to the 0 power is protected, so it's simply 1. Positive one, not the negative one. Okay? Your code for this lesson is going to be 399 on homework number 27. 399 on homework 27. Okay? All right, do your practice problems and we'll see you in class.